In the context of wearable-based human activity recognition, the authors propose a return to discrete representations via self-supervision. They leverage recent advancements in vector quantization, VQ, to directly learn a mapping between short spans of sensor data and a codebook of vectors. This approach enables the derivation of symbolic representations of movement data without annotations. The method consists of convolutional blocks for encoding sensor data, followed by a vector quantization module that replaces the encoding with the nearest codebook vector. A causal convolutional encoder is then used to predict future time steps of data in a contrastive learning setup. The authors demonstrate the efficacy of their discrete representation learning using wrist-based accelerometer data from the Capture 24 dataset, contrasting their approach against other representations including end-to-end training and self-supervised learning. The evaluation is performed on 6 diverse benchmarks, showcasing the potential of discrete representations for various activities including locomotion, daily living, and gym exercises. This research paper presents a novel approach to learning discrete representations of human movements using wearables-based sensors. It combines learned vector quantization, VQ, with self-supervised learning methods, demonstrating comparable or improved activity recognition accuracy across 3 datasets and sensor locations. The paper also discusses various computational methods for discretizing sensor data, including symbolic aggregate approximation, SAX, multivariate bag of SFA symbols, emboss, and word extraction for time series classification, WEASL. These methods have been applied in different domains such as gesture spotting, motion primitives, and speech recognition. The proposed method utilizes the Vector Quantized Variational Autoencoder, VQVAE, to generate discrete codes instead of continuous latents. This allows for a differentiable mapping of data to a codebook of vectors, which can model long-term dependencies through the compressed discrete latent space. The paper highlights the potential impact of learned discrete representations beyond standard activity recognition, including activity discovery, activity summarization, and fingerprinting for large-scale behavior assessments. In the context of speech recognition, discrete representations have shown great promise by enabling a differentiable mapping of spans of audio waveforms to a codebook. Techniques like VQ-Wave2-Vec and Wave2-Vec 2.0 represent the state-of-the-art in speech recognition, with the introduction of extensions including the use of Roberta pre-training and acoustic models for improved speech recognition. The paper concludes by discussing the potential of the new learned discrete representations for various applications and future work. This research paper explores the concept of discrete representation learning for wearable sensor data, aiming to enhance human activity recognition and provide a deeper analysis of human movements. The proposed framework involves 2 stages: pre-training, where the network learns to map in labeled data to a codebook of vectors, resulting in discrete representations, and fine-tuning, which utilizes these discrete representations as input for recognizing activities. The paper leverages self-supervised learning paradigms, such as enhanced CPC, and applies vector quantization, VQ, to derive the discrete representations in an unsupervised manner. This allows for the utilization of large scale in the wild datasets and enables the mapping of discrete representations to spans of sensor data, potentially leading to more accurate classification of activities. The manuscript discusses various self-supervised learning methods, including multitask self-supervision, transformers, and contrastive learning frameworks like SIM-CLR, BIAL, and CPC. It also highlights the potential of discrete representation learning to aid in the lower-level analysis of human movements while maintaining state-of-the-art performance in activity recognition. The paper outlines the process of adding a VQ module to the enhanced CPC framework, which involves updating the network parameters and codebook vectors using the loss from the pretext task and the VQ module. The utility of the derived discrete representations is quantitatively measured through activity recognition on downstream target-labeled datasets, utilizing a classifier network for evaluation. Here is a combined summary of pages 7 and 8 of the research paper. The proposed framework for learning discrete representations of human movements from wearables data combines a contrastive future time step prediction problem with vector quantization. The self-supervised pretext task utilizes the Enhanced Contrastive Predictive Coding (CPC) framework, which predicts multiple future time steps in a contrastive learning setup. This captures slowly varying features in the sensor data, beneficial for representation learning. The framework consists of a convolutional encoder, which maps windows of sensor data to latent representations, and an aggregator, which summarizes previous latent representations into a context vector. The encoder comprises 4 blocks with 1D convolutional networks, ReLU activation, and dropout, resulting in a reduction of temporal resolution. The aggregator is a causal convolutional network that enables improved parallelization and faster training times. Vector quantization is applied to the latent representations, where each representation is replaced with the index of the closest codebook vector. The codebook consists of V representations of size D, and the nearest neighbor codebook vector to any latent representation is chosen based on Euclidean distance. This process can be considered a nonlinearity that maps latent representations to one of the codebook vectors. The online commens-based quantization is used, which is similar to the vector quantized autoencoder. The quantization module replaces each latent representation with the index of the closest codebook vector, and the aggregator summarizes previous quantized representations into context vectors used for predicting multiple future time steps. The architecture can be adjusted to accommodate different sampling rates, and the output frequency of the encoder can be modified by changing the convolutional encoder architecture. The proposed framework substantially improves the performance of the learned representations compared to state-of-the-art methods. In this paper, the authors introduce a novel approach for learning discrete representations from sensor data using self-supervision. They propose an architecture that consists of an encoder, a quantizer, and a decoder. The quantizer maps the output of the encoder to a discrete representation by selecting the closest codebook vector. This discrete representation is then used as input to a classifier network for activity recognition. The authors also discuss the importance of preventing mode collapse, where only a few codebook vectors are utilized, and propose independent quantization of partitions to mitigate this issue. The authors utilize the Capture-24 dataset for pre-training, which contains around 2,500 hours of data from 151 participants in daily living conditions. They evaluate the performance of the discrete representations on target datasets collected at the wrist, waist, and leg. The datasets used include HHAR and myogem, which are summarized in the paper. The setup for learning and utilizing discrete representations for sensor-based human activity recognition is detailed, including data preprocessing and implementation details. The Capture-24 dataset is chosen for pre-training due to its large scale and recording setup, allowing for comparison against prior works. The authors downsample all datasets to 50 Hz, as in 31, and utilize 2 datasets per location for evaluation. Here is a combined summary of pages 11 and 12. The research study focuses on learning discrete representations via self-supervision for wearables-based human activity recognition. The study utilizes 5 datasets: Capture-24, HHAR, myogem, Mobiact, MotionSense, and mHealth, which are summarized in Table 1. These datasets vary in terms of sensor locations, number of users, and activities performed. The Mobiact dataset consists of 61 participants performing 11 activities, with data collected from a Samsung Galaxy S3 smartphone placed in a trouser pocket. The MotionSense dataset contains data from 24 subjects performing 6 activities, collected from an iPhone 6s. The mHealth dataset consists of 10 participants performing 12 activities, with data recorded from Shimmer 2 wearable sensors. The PAMAP2 dataset comprises 3 IMUS and a heart rate monitor, with 9 participants performing 12 activities. For data preprocessing, a single accelerometer is used for both pre-training and evaluation. The sampling rate of Capture-24 is reduced to 50 Hz, and all target datasets are downsampled to 50 Hz. The window size is set to 2 seconds with an overlap of 0 for Capture-24 and 50% for target datasets. The dataset is split randomly by participants at a 90:10 ratio for training and validation. For evaluation, the target datasets are separated into 5 folds, with the first fold split at a 80:20 ratio by participant into trainable and test sets. The remaining folds are constructed by randomly choosing 20% of the participants as the test set, ensuring no participant appears in more than one test set. The implementation details of the study utilize the PyTorch framework. For self-supervised baselines, the performance is reported as detailed in the original enhanced CPC paper. The discrete version of CPC is implemented with a learning rate in L2 regularization set to 1e4, and the loss weighting parameter is set to 0.25. The prediction horizon is set to k equals 10 with the number of negatives equal to 10. Early stopping with a patience of 5 epochs is employed, and a cosine learning rate schedule is used. The research focuses on learning discrete representations of human movements for wearable-based human activity recognition. It evaluates the effectiveness of discrete representations using a GRU classifier and compares their performance against established supervised and self-supervised baselines. The study explores the impact of controlling the resulting alphabet size and the effect of sensor data duration on the representations. Additionally, it applies self-supervised pre-training techniques designed for discrete sequences to improve recognition performance. The results show that discrete representations perform comparably or better than self-supervised and supervised baselines on 3 of the benchmark datasets, indicating the capabilities of the learned symbols. The study also highlights the importance of dataset choice, as performance varies significantly across different activities and sensor locations. For instance, discrete representations excel in locomotion-style activities but struggle with fine-grained gym activities. Overall, the research aims to demonstrate the potential of discrete representations in human activity recognition and derive a deeper understanding of their working. The research paper discusses the use of discrete representation learning for wearable-based human activity recognition. It compares the performance of the proposed technique, VQCPC, with established methods like SAX and SAXREPEAT. The results show that VQCPC outperforms both SAX and SAXREPEAT on various datasets, including HHAR, MyoGym, MobiAct, MotionSense, mHealth, and PAMAP2. This is attributed to the ability of VQCPC to learn a better mapping of sensor data to discrete representations. The paper also studies the impact of the maximum dictionary size on activity recognition, finding that limiting the size to 64 or 128 can result in significant performance improvements. The optimal dictionary size depends on the required fidelity and computational power. Overall, the research highlights the effectiveness of discrete representation learning for activity recognition and its potential to improve performance and reduce data upload costs. This research explores the impact of varying the output frequency of a convolutional encoder on the performance of human activity recognition in wearable-based systems. The base setup results in a discrete symbol for approximately every second timestep of sensor data. Adjusting the encoder architecture to achieve an output frequency of 50 Hz or 11.5 Hz, the study observes that the base setup of 24.5 Hz results in better performance while also reducing computational costs. A lower encoder output frequency leads to substantial reductions in performance, especially for waste-based datasets, experiencing a drop of over 20%. Maintaining the same output frequency as the input causes a smaller drop in test set performance, but with higher training times and no performance improvements. Thus, an output frequency of 24.5 Hz is preferable, allowing for quicker training and better coverage of underlying motion. The study also investigates the use of pre-trained Roberta embeddings for classifying discrete representations. By utilizing these embeddings, the performance of activity recognition improves for all target datasets, achieving state-of-the-art results for 3 datasets. The release of new techniques for text-based self-supervision can be accompanied by corresponding updates to the classification on the discrete representations learned from movement data. This manuscript highlights the potential of applying powerful NLP-based pre-training techniques to enhance activity recognition performance in wearable-based systems. Here is a combined summary of pages 19 and 20 of the research paper. The authors explore the use of self-supervision to learn discrete representations for wearables-based human activity recognition. They utilize Roberta models, specifically, small and medium versions, to pre-train on the large-scale Capture 24 dataset. The learned embeddings are then frozen and used to train a GRU classifier, with only the classifier being updated during training. The results show that using learned Roberta embeddings instead of random learnable embeddings leads to performance improvements across 5 target datasets. The small Roberta model achieves improvements of up to 2.8%, while the medium model shows similar performance, except for the wrist-based HHAR and myogem datasets, where it achieves improvements of up to 3.5%. This indicates that the increase in model size did not result in corresponding performance improvements, likely due to the dataset size not being large enough to leverage the bigger architecture. The authors also visualize the distributions of the discrete representations for each activity, plotting the histograms of the derived discrete representations per class for the train set from the first fold of motion sense. The distributions exhibit long-tailed distributions, with a significant portion of representations being used very sparsely. The impact of such a distribution is challenging to predict, as it may increase the complexity of the classifiers and embeddings due to the numerosity of rarely occurring symbols, but may also capture more niche movements that can help with classification of less frequent activities. The distributions for sitting and standing contain limited variability, verifying that the learned discrete representations correspond to the movements themselves. Overall, the results demonstrate the effectiveness of using self-supervision to learn discrete representations for wearables-based human activity recognition, and the potential for applying advancements from natural language processing to improve activity recognition. The research paper discusses the learning of discrete representations for human activity recognition using self-supervision. It focuses on the impact of the encoder network architecture and the base self-supervised method on recognition performance. The study examines the effects of varying the filter size in the encoder network and compares the performance of different self-supervised methods such as autoencoders, multitask self-supervision, and SIM-CLR. The results indicate that a filter size of 4 in the encoder network is ideal, covering sufficient motion and resulting in accurate activity recognition. Additionally, the enhanced CPC self-supervised method is found to be the most suitable for discrete representation learning, outperforming other methods by a significant margin. The study concludes that the choice of the encoder architecture and the self-supervised method have a substantial impact on the recognition performance, and that the VQCPC framework offers a promising approach for learning discrete representations of human movements. This research paper presents a proof of concept for learning discrete representations from wearable sensor data, demonstrating that the performance of activity recognition systems based on such learned discretized representations is comparable to, if not better than, when using dense, continuous representations derived through state-of-the-art representation learning methods. The proposed method involves automatically deriving the mapping between sensor data and a codebook of vectors in an unsupervised manner, which solves some of the existing concerns with human activity recognition applications based on discrete representations, including low activity recognition performance and difficulty with multi-channel data. The study highlights the potential impact of this approach beyond standard activity recognition. For instance, leveraging established methods from natural language processing, such as unsupervised text summarization, can be utilized to extract key information or summarize the most informative sensor data, allowing for a better understanding of routines and reducing noise. Furthermore, the discretization results in symbolic representations, which are essentially strings of human movements, effectively compressing the original data and requiring substantially less memory for storage. This could be helpful in situations where data needs to be transmitted from the wearable to a mobile phone or server, leading to a reduction in transfer costs. Moreover, the paper discusses the potential for activity and routine discovery. An important application includes health monitoring, where typical healthy behavior can be characterized by such discovery algorithms, whereas they may be difficult for humans, including experts, to fully specify. Discovering motifs is easier in the discrete space, rather than raw sensor data space, as the simplification to a smaller alphabet aids with the identification of recurring patterns. Especially for multi-channel data, such as accelerometry, the proposed discretization method can be useful for discovering the characteristic actions across all 3 channels, without having to, for example, perform principal component analysis to reduce the dimensionality to a single channel as in Peruse. The paper also explores recognizing fine-grained activities. It is observed that utilizing an LSTM or GRU classifier for recognizing locomotion and daily living style activities at the wrist and waist is highly effective, resulting in the best, or similar to the best, performance for 3 benchmark datasets. However, the loss in resolution due to the mapping to a small set of discrete symbols negatively impacts scenarios where the fine-grained activities need to be recognized, e.g., fine-grained gestures. Therefore, a current limitation of the proposed discretization method is that it is not yet well suited for applications, which require the discrimination between highly similar movements. Consequently, potential future work could include exploring Gumbel's softmax vector quantization and additional losses that can promote diverse codebook usage via additional losses. This could likely aid more fine-grained movements to be represented by their own symbolic representations, resulting in improved recognition. The research focuses on developing a novel approach for wearable-based human activity recognition by casting the multi-channel time series classification problem as a discrete sequence analysis problem, similar to natural language processing. This involves the use of powerful NLP-based pre-training techniques, such as Roberta, to improve activity recognition for various target datasets. The study demonstrates the effectiveness of this approach by achieving better representations through explicit control of the maximum dictionary size. The methodology leverages self-supervision, utilizing techniques like masked reconstruction and contrastive predictive coding to learn discrete representations. The results show significant improvements in activity recognition, highlighting the potential of this approach for real-world applications. The research also discusses limitations and future work, emphasizing the need for further exploration into the integration of other modalities and the development of more robust evaluation metrics. The research paper discusses the application of self-supervised learning for wearable-based human activity recognition. It proposes a novel approach to learn discrete representations of activities using self-supervised methods. The authors draw inspiration from various fields, including time series analysis, data mining, and machine learning. They discuss the importance of efficient algorithms for discovering patterns in time series data, highlighting works such as SACS and Shapelets. The paper also touches on the concept of contrastive learning and its potential in improving activity recognition. It references several studies on wearable-based activity recognition, emphasizing the need for efficient and interpretable methods. The author's approach aims to bridge the gap between the complexity of human activities and the simplicity of wearable sensors, ultimately enhancing the accuracy and efficiency of activity recognition. This section presents supplementary visualizations and mathematical formulations supporting the self-supervised learning approach for wearables-based human activity recognition. Figure 7 displays the histograms of discrete representations per class for the first fold of the MotionSense dataset, showcasing the full range of symbols. This figure is an extension of Figure 6, which truncates the z-axis to 50 symbols. Figure 8 illustrates the weight updates of the VQC-PC architecture, a critical component of the proposed self-supervised learning framework. The aggregator network is updated using the sum of contrastive predictive coding losses, denoted as n-ary summation k equals 1 klcpck. In contrast, the codebook vectors are updated based on the Euclidean distance between the stop gradient vector Sg, z, and the quantized vector z, represented as parallel Sg, z, minus z parallel 2. The encoder is updated using a combination of both the contrastive predictive coding losses and the commitment loss, which is proportional to the Euclidean distance between the original vector z and the stop gradient vector Sg, z, denoted as gamma parallel z minus Sg, z, parallel 2. These visualizations and mathematical formulations provide insight into the inner workings of the VQC-PC architecture, highlighting the distinct roles of the aggregator network, codebook vectors, and encoder in learning discrete representations. By leveraging self-supervision, the proposed approach can effectively recognize human activities from wearables-based data without relying on manual annotations.